Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to the Matric revision program. My name is Daniel Matthews, and today's lesson is, of course, physics paper one. And if you see that also in the stream, that is Mr. Muntasir Qadri, who holds a BSc in chemistry and is a private tutor at Intune. If you have any notes that you may have missed during the stream, you can, of course, check the description. There's a link there, and you can go for that link at Intune tutoring.co.za with a special link that we have there. That's just in case you miss any notes and you want to catch up. But anyway, I'm talking way too much. Assalamu alaikum wa rahmatullahi wa barakatuh to you, Masjid.
Wa alaikum salam wa rahmatullahi barakatuh, Daniel. How are you doing today?
Doing good, and you?
I'm doing great. Absolutely great. Can't complain. Had a lovely, relaxed weekend and looking forward to
Oh, that's
tackling
amazing.
some questions for the kids.
I just saw the paper there. I'm getting some PTSD flashbacks to the harder days of me doing fix. But with that, I'm not gonna stay too long because Muntasir is the person who's gonna be guiding you through that. I could never assist the kids. Go ahead.
Okay, shukran. So, today we will be looking at physics paper one. Specifically, we will be working on question two problems, and these involve mechanics, usually Newton's law, as you can see here. So, we'll have these blocks with some tension ropes. There'll be force, and we'll have extra blocks over here. And of course, you need to do free body diagrams, and that requires you to have a certain basic understanding of the foundations of physics. So we'll go through these problems and we'll attempt them together. So the first problem we're looking at here is a 20 kilogram block resting on a rough horizontal surface. Very important to note that sometimes there are keywords that pop up. One of them is rough. And usually when you see the word rough here, that's telling you that friction is going to be involved. Right? So, is connected to blocks P and Q by a light inextensible string moving over a frictionless pulley. Block P and Q are glued together and have a combined mass of M. That's over here. P and Q with a combined mass of M. Here's our 20 kilogram block. Here's an applied force of 30 newtons at an angle of 40 degrees. And we can see that this P and Q mass that's together are being pulled down in this direction by gravity, but being held up by the tension on this rope over here. But we'll do the diagrams and we'll see what's happening. A force of 35 newtons is now applied to the 20 kilogram block at an angle of 40 degrees with the horizontal as shown below. There's the horizontal, right? The 20 kilogram block experiences a frictional force of a magnitude of 5 newtons as it moves to the right at a constant speed. So, the fact that it's moving to the right at a constant speed, firstly, that tells us that there is what? Constant speed, no acceleration, right? That's what that means. Okay, and there's the friction that we spoke about because they mentioned a rough horizontal surface. So the first part of this question is a definition question, 2.1. Define the term normal force. And your normal force is basically the force applied by the surface onto which the object is touching. And that force is perpendicular to the surface. Right? Perpendicular meaning it is at a 90-degree angle. Right? So it's perpendicular to that. And this would be your normal force. Right? And that's basically the definition of a normal force. And we can look at the memo to see what they said for the definition. I'm sure it's basically the same. Let's just take a look here, scroll down. And here we go. The perpendicular force exerted by a surface on an object in contact with the surface. Right? Basically what we did. So as long as you're saying perpendicular force and you say something like exerted by a surface on an object, then you will get your 2 marks. Now, let's go back up. Now, 2.2, draw a labeled free body diagram of the 20 kilogram block. So, if we had to draw a free body diagram for this, it would look something like this. So, let me just get a different color. Yellow is a bit hard to see. Give me a second. Let me go here. Let me just switch to black. Okay. Now, I'll just draw it on the side over here. So, we need to draw a free body diagram. Now, this is, I'll draw my free body as a circle, right? Some sort of particle. And this particle represents the 20 kilogram block. I'm just making it very simple. Now, To draw this free body diagram, we need to imagine all the forces acting on this block. Okay, we know we have a normal force acting upwards. We know we have the weight of the block or the force due to gravity, right? So depending on what school you're in, you'd either say W for weight, or you'd call it Fg, the force of gravity, right? That's pulling it down. And then we have an applied force over here of 35 newtons at an angle of 40 degrees, right? And we'll call this Fa because it's the applied force. And over here, we have a string, right? And this string is being pulled to the right. And we can call that tension. And of course, that would mean our free body diagram would look something like this. Now we just input the information on the diagram. And we just go here. That is the normal force. This is Fg. I'll just do this quickly. There we go. Just make a horizontal plane. Here's our applied force, Fa. And here's our tension on the string. Right, and this should be for 5 marks. Let's see if it matches. Scroll down. Let me clear this off. And oh, one more force I forgot. And I mentioned it in the beginning. Frictional force. Right? They mentioned here about the frictional force of magnitude 5 newtons as it moves to the right. So if the object is moving to the right, the frictional force is always opposite to the direction of motion. Right? So that would mean our frictional force would therefore be to the left. Right? Fr. Right? And that's what it would be over here. Fr. And that's our free body diagram. Very simple. These are not hard to do. Just be careful with your information. What I would say is write down everything that's given to you before you even try to do it. So for example, you can have a section here called given. Right? I like to do this. I like to say there's a section called given and a section called to find. Right? And that's what you're searching for. And if you categorize your information like this, it kind of makes things a lot clearer as to what you need to do. So this is basically what our free body diagram is. And that's pretty accurate. So let's go on to the next question. That's our free body diagram done. The next question, calculate the combined mass M of the two blocks. So they want us to calculate this combined mass. And we can see that this is for 5 marks. Right? So of course, let's take a look and see if we can solve this problem. So we can essentially separate this into 2 parts. Okay, so let me do this. So in order to work out this mass over here, we'll need to find the tension on the string, right? And that will assist us in solving the mass of this block over here. Now, what we can do is, let me just, there we go. Let me just copy this, add it to a new page. Okay. Now, we will need to separate this into 2 parts, right? There's an object over here that needs to be focused on, and there's a separate object over here that needs to be focused on. Now, of course, we're going to have therefore 2 free body diagrams, one for this object and one for this object. Okay, now let's take a look. Let's first do the 20 kilogram block again. We'll do this, right? And what I like to do as well is I like to insert Cartesian planes. The reason being is to help you keep track of whether or not, of what your reference points are. All right, so I'll do this. Just draw a Cartesian plane for this one, for the 20 kilogram block. So we'll first work on the 20 kilogram block. I'll do this, this, and this. I call this X. I'll call this negative X. I'll call this Y. I'll call this negative Y. So what I've essentially done here is I've chosen the right as positive and up as positive, and I've chosen the left as negative and down as negative. So therefore, any forces that exist in the left or down will all have a negative value. Remember that these are forces, they are vectors, they have both magnitude and direction. Direction can be indicated by the operator. So in this case, my operator, the negative, is telling me that the force is acting to the left. A positive operator indicates to me that the force is acting to the right or up. Now let's insert our information. So here we have the normal force acting up. Okay. And of course, we're going to need to calculate this information. We've got our Fg acting down. We have our tension to the right. We have an applied force at an angle of 40 degrees. Let's insert this here. And we have a frictional force over here as well, Fr. Right? This is Fa. Now, let's input some important information. Fa is 35 newtons. So we have that force. We know that Fr is 5 newtons. Right? We've got Fg over here. Well, let's solve for Fg. Fg is 20 kilograms. And if we had to solve for Fg, we would basically say Fg is equal to our mass times the gravitational constant. On Earth, that's a 9.82 meters per second. We'll just use 9.8. And we'll just go here 20 kilograms times by 9.8 meters per second minus 2. Now, they might not place, I don't know how some schools are, but I remember when I was at school, they didn't place a lot of emphasis on putting the units in whenever you're solving the problem. My advice is always put the units in. Reason being is this will help you. By doing this, you will subconsciously then remember what it is that a specific force is made up of. So the answer here is now 20 kilograms. Oh, where's my calculator? Give me a second. Here we go. Oops. Okay. So 20 kilograms times 9.8 is going to give us 196 kilograms. Now, I know you're not used to seeing it like this, but kilograms meters per second squared is the same as 196 newtons. It means the same thing. Okay, so we can put this in. Oh, this is 196 newtons. And the normal force is always opposite, right? Is always going to be the same value as the force acting down. So our normal force is also going to be 196 newtons. And there we've solved the normal force. Okay. What we don't have, though, if you notice, we don't have the value of the tension in the string. So therefore, this is something that we're going to need to calculate. Now, what you can do, right, is some people struggle with identifying, with taking forces and turning them into the components. And you will notice that, of course, okay, tension won't have any components. It's already in the horizontal. Our normal force and our force due to gravity won't either because it's already vertical. But if you look at the force applied, it's at an angle of 40 degrees. So this actually means that this force has a vertical force that's applied, and there is a horizontal force that's applied. Right? We'll call this FAY, and I'll call this one FAX. Right? That's the horizontal force applied. I mean, notice tension exists where? Tension is a force that's been pulled in the horizontal. So therefore, what does this tell us? If tension is only a force that's been pulled in the horizontal, and we want to find tension, which is only on the x-axis, we only need to work with vectors that exist on the x-axis. So what vectors do we have that exist on the x-axis? Let's take a look. We have friction, which is 5 newtons, but it's to the left, so I'll call it negative 5 newtons. Right? We have our applied force here, so we need to calculate FAX still. Right? And let's go ahead and do that. So FAX we can solve. I'll just draw a red line here, okay, indicating that this is the same force as this over here, but I'm just making a right angle triangle, so we can use Pythagoras to assist us in solving this problem, or we can just go straight ahead to trigonometry. In this case, we'll go straight ahead to trigonometry. We can see this is 40 degrees. This is adjacent, which is the angle we want. This is opposite. This is hypotenuse. We have the hypotenuse value, but we don't have the adjacent value. So therefore, what does that tell us? That if we want to find f of x, right, a over h is cos. So we just say cos 40 degrees is equal to a over h. I'll write here a over h. A is what? f of x, right? Force applied on the x-axis over our hypotenuse, which is 35 newtons. And there we find that f of x is actually equal to 35 cos 40 degrees. And what is 35 cos 40? Let's check. That is going to be 26.81 newtons. Okay, now let's go ahead and look at the memo so long and see if we are up to date and we're on par with this. Let's see. All right, so we need to find the tension, which is what I suggested. Right, and there we're using fx t minus f of x equal to ma. Okay, now if we go back here, so we are on the right track. So if we go back here and we look at this problem, so there's of course in the horizontal there's a net force, right? And we know that there's a net force, and the net force is pulling this block to the right. We know that, okay? But we don't know the value of the net force. But we can use all the information given to us. So we got F net, and specifically for the x-axis, because we're working with those things, is actually equal to, and we can put these things together. We can add FAX plus FR, which is friction. And what's the other force in the horizontal? We got friction, FAX, plus T. Right, so these are the three forces we need to use. Right? I know I'm showing plus, I'm adding them all together, but you'll see why it's important to label the axes, because these operator signs will change once I input the information specifically according to the reference that we've given. Right, so they've given us that. Let me just go back to the question. Do they state anything else that we need to use? A 20 kilogram testing surface connected to blocks. Right. A force of 35 newtons is applied to the block. Yes. Okay. Right. That's all fine. Okay. So here we go. They got F net equals m times mass times acceleration. Right. We got T minus F of x equals ma. Now note there was something very interesting they told us. Remember, they told us that there was no acceleration. They told us there was a constant speed. Right. So if we go here, because there was a constant speed and no acceleration, right, we know that F net is also equal to mass times acceleration. Now, something important to note. If your speed is constant, then your acceleration is equal to 0 meters per second squared. So what does that tell us? That means that our net force is actually going to be 0 meters, 0 newtons. And how do we know this? Well, we've got an acceleration of 0. So therefore, F net is actually equal to this 20 kilograms times by 0 meters per second minus 2, which equals 0 newtons. So we know that. And we got this equation to work with. So we can therefore say that 0 newtons is equal to FAX plus FR plus T. And we want to solve for T. So we can rearrange the equation and say that T is equal to negative FAX plus, the FR moves over, minus FR. Right, so I'm just doing some algebraic manipulation and resolving the equation so that t is the subject of the formula. Now, all we do is we substitute the values in, but remember the references, right? So FAX is being pulled to the left, so therefore it's a negative value. So we can just go negative, we worked it out to be that, negative 26,81. And you'll see our answer will turn out to be positive because our tension is pulling towards the right, which makes sense. Minus our frictional force, which is negative 5 newtons. That gives us 26,81 plus 5 newtons. Now we find that our tension will be 26,81 plus 5 is 31,81 newtons positive to right? So therefore this is to the right. And now we have solved the tension. We've solved the first part of our problem, finding out what this tension is. Now, here's the trick. If the tension here is 31.81 newtons, right? That means that the tension here is also 31.81 newtons, right? And that's going up. But we also have the force of gravity being exerted on this block. However, we know that it's moving at a constant speed, so there's no acceleration. So we know that the net force on this block will also have to be 0, but in the y-axis. Okay, so therefore we can work out Fg and then therefore work out the mass of the block. So if I just go to another page, let me do this, and I'm going to draw another free body diagram. I'll just put this in here. Right, so this was P, this was Q, and we got a free body diagram here. We got Fg, we've got this tension here, right? We know that the speed is constant, so therefore acceleration is equal to 0. Therefore, F net y is equal to 0 newtons. So therefore, F net for this is equal to T plus Fg. So this is pretty simple to solve. So therefore, if we want to find Fg, Fg is equal to negative T, right? Because we're going to rearrange the equation because the 0 is over here. So we just put the T over. But we calculated T, didn't we? So T will just be, if we go back here, the value was 31.81 newtons. So negative 31.81 newtons. Now, we need to solve for this. Fg is equal to mass times gravity. And this is the mass for P and Q together. So we can solve this. So therefore, mass is equal to, now remember this is negative 31.81 newtons going down. So it's negative here, right? So we can just say, we can make, let me just quickly rewrite this, so it makes more sense before I confuse you. So this is the same as saying Fg is equal to 31.81 newtons downwards. That's what the negative tells us. It tells us about the direction. Remember that. Our operators tell us about the direction of the vector. Now, Fg is equal to 31.81 newtons downwards. And what does this mean for us? We can then calculate our mass times gravity is also equal to 31.81 newtons. We know gravity is 9.8, so we can say mass is equal to 31.81 newtons divided by 9.82. Right, and this is meters per second minus 2. Now, the reason I say it's always important to put the units in is for this. We can see that we have newtons here, meters per second there. We know mass is measured in kilograms. But let me show you something a little bit interesting. I'll just do it as a side note over here. Newtons is the same as kilograms per meters per second. What does this mean? If we make that kilograms per meters per second over meters per second, where mass is equal to this, notice the meters per second cancel each other out, and we're left with a unit in kilograms, which is what mass is measured in. Just so you can understand the reasoning behind why it is your answer comes out to what it does. Okay? Just a little bit of backdoor information there. And we can solve this. So 31.81 divided by 9.82 is equal to 3.24 kilograms. Now, let's see if our answers match. Let's take a look at the memo. And there we go, 3.25 kilograms. Right? And we solved it exactly as they requested. And that would have been for 5 marks. Easy peasy lemon squeezy, not too hard. Just follow the information and follow the instructions, and you'll be perfectly fine. And of course, practice. Practice is extremely important. So we did that there. We calculate the combined mass of the 2 blocks. And they say in 2.4, at a certain stage of the motion, block Q breaks off and falls down. How will each of the following be affected when this happens? Will the tension in the string increase, decrease, or remain the same? So, what do you think will happen? If Q is breaking off, this block disappears. The mass is decreasing over here. Right? We still have this force of 35 newtons being applied, but this mass decreased. Oops. So let's see what they say in the memo. They tell us it's going to decrease, and that makes sense, right? If we are losing mass, this mass is applying a specific amount of tension downwards on the string. If we remove a block, there's going to be less tension on the string. It stands to reason, right? And therefore it's going to decrease. Well, what's the next question? How will each of the affected? The velocity of the 20 kilogram block. What will happen to the velocity? Well, this is for 3 marks. Let's take a look at the memo and see what they say. As the tension force decreases, the net force acceleration acts in the opposite direction of motion to the left. Okay. And they say the velocity increases. So as the tension force decreases, the net force or acceleration acts in the opposite direction of motion to the left. Opposite to the left. So, oh no, they're telling us it's moving to the left. My apologies. I'm getting confused by this memo. Right. So if we look at this, let's go back here. So first thing we discovered, let's do this. They tell us, so in the original situation, right, where it was P and Q, we had a certain tension. We'll call it T1. Now, in the next scenario, Q is gone, and it's just P. We still have tension. We still have this mass. But of course, we now find that this is tension 2, but tension 1 is greater than tension 2. Right? Obviously, because of the mass that's missing. We know tension is a force, and force equals mass times acceleration. Force equals mass times acceleration. Tension also equals mass times acceleration. We can see that tension is directly proportional to mass. So what does this mean? This means if we decrease mass, we will decrease tension. Right? So you can actually use these equations to directly correlate the scenarios that we're looking at. You can make a direct correlation. Let me just clean that up, right? And then in the next part, they say the velocity of what happens to it. So we found that the velocity increases. Okay. in the opposite direction. So they say to the left, which makes sense, right? Because remember, there was a net force of 0 here and a net force of 0 here, right? And this extra weight was slowing down how quick, slowing down well, yeah, it slowed down the velocity at which we could pull this 20 kilogram block to the left. But if we remove this weight, it makes it easier, and the velocity will speed up. It stands to reason. It's the same idea as, let's say we have a person over here, right? Let's say you do, I don't know, calisthenics or some kind of exercise. I'm sure you've seen this where people tie a tire to themselves, right? And let's say we had some weight on here and we asked you to run to the left, right? You with the weight on your tire, depending on how strong you are, but let's say these two individuals are the same strength. If we give this person just the tire, this person here will move a lot faster than this person here, and that's because of the weight that is not on it. And that's the same concept that's happening here. Because the weight has been released, right? What will happen is the force pulling in this direction has less resistance to deal with. There's less mass to deal with on this end, causing this tension here to slow this force down. And therefore, we'll be able to increase in speed to the left. Right? So, let's go on to the next one. Okay, we still have some time. Let's take a look. Okay, next question. So it's basically going to be the same concept. And here we go again. And once again, I will place emphasis on this. Always insert your units when you're doing calculations, and always conceptualize the problem. Draw your free body diagrams, indicate your directions. And another thing, always write down what they're asking you to find and what they're giving you. Okay, it's like playing Sherlock Holmes. So here they say, state Newton's second law of motion in words. This is some basic theory, and everyone should be familiar with this by now. And they basically state here, when a non-zero resultant force acts on an object, the object will accelerate in the direction of the force with an acceleration that is directly proportional to the force. This makes sense. This comes from that equation, force equals mass times acceleration. Right? So the object will accelerate directly proportional to the force that is applied. We can see force is directly proportional to acceleration. It is also directly proportional to mass. Now, what else do they state? And they say, and inversely proportional to the mass of the object. Okay, that makes sense because they're speaking about the formula in this form. We know force equals mass times acceleration. Right? But if you make acceleration the subject of the formula, we'll get acceleration equals force over mass. And in this form, you can see that acceleration, as they state, is directly proportional to force, but inversely proportional to mass. When it's 1 over m, that's an inverse proportion. Okay? Now, let us look at the next question. Where are we? Okay. Draw a labeled free body diagram for the 8 kilogram block. Okay, first off, let's find the clues that they give us. They say an 8 kilogram block on a rough hard. There we go again, a rough. So we know we got friction we're working with, right? So immediately I'll just write it over here for given. We know we're going to have friction somewhere. It's connected to a 2 kilogram block. Okay, there's a 2 kilogram block by a light inextensible string passing over a frictionless pulley as shown below. The 8 kilogram block moves at a constant speed when pulled by a 29.6 Newton horizontal force to the right. The frictional force acting on the 8 kilogram block is 10 Newtons. Now, once again, I'm going to choose right as positive and left as negative. This is us making a reference. So I know my friction, I know we're pulling the block to the right. So my right is positive. This frictional force is always acting to the left. So that's negative 10. Our applied force is 29.6 newtons. Right. Now, let's quickly draw this free body diagram for the 8 kilogram block. Here's my 8 kilogram block, a lovely little particle over there. We know we have Fg acting down. This is the force due to gravity. We have the normal force, which is always perpendicular to the surface that the object is in contact with. That's our normal force over there. We have the applied force directly to the right. And this is equal to 29.6 newtons. We also have our frictional force being applied to the left. And with that, well, I know our tension is going to be greater, so I'm drawing a longer arrow. There is the tension in the string. And this is the free body diagram that we will need to use. And if we take a look at the memo quickly, does it match? Let's take a look, and there we go. Right? Beautiful. Fits in perfectly. Now, clear this off. Next part of the question. Calculate the tension in the string. Easy enough. Once again, what are they telling us? Constant speed. There's that word again. So when we see the words constant speed, we know that acceleration is equal to 0 meters per second minus 2. Very, very simple. Now we go ahead. Now we know that F net, right? It's the sum of all the forces. And we're specifically looking at what? The sum of all the forces in the horizontal. We can completely ignore our normal force and our force due to gravity because our tension is strictly on the x-axis, got nothing to do with the y. So we focus on these three forces. So we can say that F net is equal to the force applied plus tension plus Fr. Now, I can go here. I know my force applied to the right, so it's 29.6 newtons. My tension is unknown. We still need to find that. And my frictional force is going to be negative 10 newtons. Okay. F net, our acceleration is 0. That means that our F net is also equal to 0 newtons. Right? Because F net is mass times acceleration. And if our acceleration is 0, we will have a 0 net force. So we can go over here and say 0 net force. Now we can solve for t by making t the subject of the formula. It's the only variable that's existing. And we can go ahead and say t is then equal to, we move the 29 over, negative 29.6 newtons. We're moving this negative 10 over, that becomes positive, plus 10 newtons. And our answer for our tension is going to be negative 19.6 newtons, or 19.6 newtons to the left. Does our answer match these? Let's double check. Let's see if we're on the same page as them. And where is this information? There we go, 19.6 newtons. Perfect. We matched everything up. All right. Now, the next part of the question. Right, we calculated the tension. So 3 marks, easy peasy lemon squeezy. All we had to do was set up F net, say that's the sum of all the forces acting in the horizontal because we were specifically working on the x-axis, and we just had to say that F net was equal to 0 newtons because they told us this is moving at a constant speed. There's no acceleration. Okay. Now, the next one, 2.4. Apply Newton's second law to each block and calculate the magnitude of the acceleration of the 8 kilogram block. Okay, so there's something else that got added here. The 29.6 Newton horizontal force is now increased to 50 newtons. So this has changed. This horizontal force is now 50 newtons. Okay. So we went from 29.6 newtons all the way up to 50 newtons. This changed. And so, of course, if we're increasing that, applied force is going to have a different effect. We're definitely going to be pulling this faster. Okay. Now I want us to calculate the magnitude of acceleration on the 8 kilogram block. So let's quickly take a look at what they did. I don't want to sit too long because we're almost out of time. So let us just analyze what they did for the solution. And if we look here, 2.4.1, right? They went ahead, and let me zoom in actually. My apologies. I think I should have zoomed in long ago. Okay, let's just clear this off. And here they state that F net equals mass times acceleration, which is true. We always use that formula. Here's the 8 kilogram block that we're specifically looking at. Now we go ahead and we say 50 newtons minus 10 minus T. We don't know what the tension is now, but we need to find out. Equals 8 times acceleration. So we have two variables, tension and acceleration. We're going to end up with a simultaneous equation here, right? Because we've got two variables in this first equation. So this is equation 1. Then we go ahead and we look at the 2 kilogram block. And we follow the same procedure. F net equals mass times acceleration. We can say F net equals m times a. We don't know the tension. We do know mass times gravity is 2 times 9.8. The mass for the block is 2, so we put the 2 in there, and there's acceleration. Once again, two variables. Now what do? All we do here is we set tension on either side as the subject of the formula. They didn't put it in the memory here, but I'll show you. And what they did was this. They said T is equal to, hold on, I need to keep T positive. So I'll move T over to the right and the A to the left. And what we'll end up with is T is equal to 40 minus 8A. Right over here. This will be our equation 1. And our equation 2 over here will be T. They used 40 newtons over there. Okay, they say T is equal to 2A plus 19.6. Now look at what we do here. We've got T and T. The tensions are the same, no matter if it's, as long as there's the same string, the tension will actually be the same. So we can set these two equations to be equal to each other. We can let 1 equal 2. And we'll end up finding that we can go 40 minus 8A is equal to 2A plus 19.6. Okay. I will move this 8 over. We'll get 10A is equal to, I'll move this 19.6 over, and 40 minus 19.6 is 20.4. And what do you know? Look at that. 20.4 equals 10A, 10A equals 20.4. And we'll find that A is equal to 2,04 meters per second squared. And that's the acceleration that we've gained due to the increase in force. Right. Let's look at the next one over here. Let me just scroll up. Now, the last part of this question. Right, we calculated the magnitude of acceleration, now the tension in the string. And all we do is we use the acceleration that we calculated to assist us in solving the tension in the string. And if we go over here, we just use the previous formula. We can choose one, 40 minus T or any one. Right, so here they used 40 minus T equals 8A. They put this value in, and Bob's your uncle. There we go, 23,68 newtons. Very, very simple. You literally just substitute the value that you found here into one of the formulas that contain tension over here, and you'll be able to solve the problem without a hitch. Okay? So that concludes our session for today. If you would like to view these questions and the memo, it is available on the website www.intunetutoring.co.za. There will be a special link provided by the Voice of the Cape that you'll be able to use to access this. And yeah, if you have any other further queries, you can contact this number as well, or you can just just contact this number. This is just the website, so I thought it was an email. Just contact this number if you have any further queries with regards to tuition. Yeah, that concludes our session for today. I hope that it was educational and that I helped you. And yeah, that's it. Assalamu alaikum wa rahmatullahi wa barakatuh.
Shukran so much, Mutasir, for that excellent lesson. I'm sure everyone is better off. I would say everyone, however, I myself didn't understand most of what you were saying. So, so there's definitely one person that didn't get it. But alhamdulillah, this will be up on our Facebook and YouTube for quite a while. So even if somebody forgot or maybe they didn't quite catch something, they can still rewind and check back in. But shukran so much, Mutasir, for coming on. It's truly been a blessing.
Afwan, not a problem. Shukran for having me. Hope you enjoy the rest of your day, Daniel.
Will do, and you too. Anyway, for all of the
Shukran.
wonderful watchers, I'd say assalamu alaikum to you. Tune in tomorrow. I believe tomorrow will be mathematics. So stay tuned for that. Assalamu alaikum.
Walaikum salam.